Right. Good afternoon, everyone. Very warm welcome to the second session. Now, this particular session is focused on open quantum systems and non-Markovianity and essentially how quantum systems reach equilibrium. I mean, equilibrium statistical mechanics, equilibrium thermodynamics, they're kind of well understood. But from the quantum perspective, how quantum systems connected to a bath or isolated quantum systems, how do they reach steady state or equilibrium? This question has been partly answered. We know, I mean, most of it probably, but then there are a lot of unknowns. We do not know a particularly strongly coupled system, how do they go to equilibrium? So this is one aspect that we would like to study as part of this foundational exploration of quantum mechanics. So this session, we have two speakers. Our first speaker is Professor Francesco Bouscemi. He is from Nagoya University, Japan. So about the speaker, he did his PhD from University of Pavia. And Francesco, you are there. Can you hear me?
Yes, I can hear you now. Yes.
Wonderful. And he is audible from the back. Can you hear him? No? Can you raise the voice maybe, Francesco, a bit? All right. Can you go again, Francesco?
Okay.
I continue. So he did his PhD from University of Pavia. Then Francesco did a postdoc at Irato-sourced Quantum Computation and Information Project in Tokyo, Japan. Then he was in the statistical laboratory of University of Cambridge. So Francesco mostly works on quantum statistics, quantum thermodynamics, quantum entanglement, many branches of quantum mechanics. And for his work, he was awarded Markov von Neumann Prize in 2018. So it is great that he agreed to give us an overview of open problems related to open quantum systems. And Francesco, over to you.
Okay, thank you very much to the chairman for this introduction, Professor Bhattacharya, and I would like also to thank the can you hear? Yeah. Also the other organizers, Professor Hom, Professor Banerjee, Dr. Bera, Dr. Bonik, and also Dr. Singh for this opportunity. I have been looking forward to this event for months, but unfortunately a last-minute family-related complication prevented me from joining you. This made me very sad. Okay, I hope I can make it up with this online presentation. So let me share the first slide. Okay, so I will try to introduce one of the main problems. So there are many issues with the open quantum system dynamics. But I would like to focus on one particular problem on one particular problem, which is the problem of non-Markovianity and the problem of how to define the reduced dynamics of a system when there are initial correlations possibly between the system and the environment, and then the two go through joint evolution. So in order to understand how to model the evolution of an open quantum system, we should start from the evolution of a closed quantum system. And this is given as a postulate, if you like, by Schrödinger's equation, which tells us that a closed or isolated, okay, depending on the subfield you're working within, sometimes you might use the word closed or sometimes the word isolated. Anyway, what Schrödinger's equation tells you is that the system evolves by unitary evolution. So you have the initial state here at time t0, the final state here psi prime at time t1, and the relation between the two is a functional relation represented by this unitary evolution. So the important point to understand here is that this has a Markov property built in the sense that the state of the system at time t1 depends only on the state of the system at time t0. and not on, for example, on its past history or how the system has reached the state at time t0. The only thing that matters is the state, the instantaneous state at time t0, and that's all you need to predict what will be the state of the system at the later time t1. So then, if you are interested about the evolution of an open system, you can somehow reduce the problem to the problem of a closed, enlarged system if you believe in the possibility of closing your system. So there is an assumption here, which is the assumption of closability, that would be like saying that any open quantum system Q can be closed if you take into account enough parts of the universe, those parts that we call the environment, that interact with it. So essentially, if you take into account the entire past cone of the system Q prime, you should be able to close somehow your system. So the idea is that you start with some open dynamics, and you're able to close the dynamics by taking into account everything that interacted with the system, all right? But now the problem is, how do you model the initial joint state? Okay, because you can say that the evolution, yes, can be closed into a box. It is similar to what you do in thermodynamics, that you say you have some thermodynamic process, and then you can always bring parts of the thermodynamic universe within the same adiabatic box, okay? So you can close this open process into a box, a unitary box, but now we have to understand how to model this situation here, the initial situation, the initial condition. Okay, so what about the initial joint state, and what about the Markov property? So textbooks, if you open a textbook on open quantum system, for example, the Breuer-Petruccione textbook, you will find that many of these textbooks start with the factorization assumption. So the initial assumption is that the system Q and its environment E begin in a tensor product state. And that's a very good reason for this, a very good, I would say, mathematical reason for this. And the reason is that in this case, so if the system starts in a state that is completely uncorrelated, completely independent from that of the environment, then the reduced dynamics of the system, what we call the open systems dynamics, is always well-defined. Well-defined means that there exists a completely positive and trace-preserving linear map that we call quantum channel, okay, that is able to describe this input-output relation. So again, you have the guarantee that the process is Markovian, in the sense that even though it is open, so even though it involves interaction with an environment, still the state of the system, of the reduced state of the system at late time t1, depends only, can be computed, can be predicted, I would say, knowing the state of the system at time t0 and nothing else. If you know, of course, if you know the channel. So this is the usual assumption, but this assumption has been challenged. I would say that the first situation that I'm aware of in which this initial factorization assumption has been challenged is in this famous physical review letters by Petrucas, published 30 years ago, that puts forth the idea of what happens if we drop the initial factorization assumption. And this paper is particularly famous for the comment it received from Robert Alitsky, arguing about the role of the assignment map. I will talk more about this point in the next slide. But for the time being, we say that essentially this problem of dealing with possible non-zero initial correlations was presented to the community 30 years ago by Petrucas. 10 years after Petrucas' paper, Sudarshan and his group actually started constructing explicit counterexamples where indeed you can have initial correlations between system and environment and yet come up with a well-formed quantum channel for the reduced dynamics. This was a time of this was a time in which a lot of groups actually went into this problem, and it was also the time in which quantum discord was particularly important and was a hot topic in the community. And the crown jewel of the literature about quantum discord was this paper published in 2009 by Shabani and Lidar. This also is a Physical Review Letters, claiming that quantum discord would essentially solve the problem, in the sense that they would have a claim, a statement in this paper, saying that the reduced dynamics of the system would be completely positive and trace preserving, so it would be well formed on its own, if and only if the initial correlations between system and environment would have zero quantum discord. But unfortunately, this claim was later proved wrong by means of explicit counterexamples provided in 2013 by Broduch and al. And this also caused some debate in the community. So somehow this idea of dealing with initial correlations between system and bath has resulted in a little bit like complicated set of works. And I would like, first of all, to try to see the historical approach to solving the problem of initial correlation, and then another possible approach to this, which makes things a little bit easier to understand, a little bit more general. So the approach that started with the paper by Pechukas and the comment he received from Robert Alitsky was based on the concept of assignment map. So they would postulate that the initial conditions, so the initial joint conditions of system and environment together, should be given as a linear, completely positive map that would lift the state of system Q to a state of the joint system Q and E together. And this assignment map should satisfy, in particular, a consistency relation. That is to say, whenever you start from a state of the system Q and you lift it up to a joint state of system and environment together, then by taking the partial trace of on the environment, you should go back to the point you started from. Okay? Then if this is a map which is well-defined and completely positive, then of course you can follow the evolution here on the level of the joint evolution. So you would have a unitary evolution here, and then conclude the cycle throwing away the environment after the joint evolution. And this would, by construction, because this would be the composition of three completely positive maps, would give you a completely positive map for the system alone. So essentially, according to this approach based on the assignment map, the entire problem would reduce to understanding the properties of the map A. However, this consistency requirement in particular, if you think about it, is very restricted, right? I mean, if you have a natural mechanism that causes correlation between system and environment, typically such mechanism, such interactions would not satisfy consistency. If you have an interaction between system and bath, most likely the state of the system after the interaction is different from the state of the system before the interaction happened. So we would like to get rid of this consistency relation and try to have a more general formalism, but which is still, amenable to mathematical study. So this is the preparability approach that I proposed back 10 years ago. So the idea is the following. So first of all, we have to understand that when we say, okay, we want to understand the initial possible conditions between system and environment, what it means. It means that we have to give a set of possible states, this sigma QE, and there is this set SQE, which is in general a subset of all possible states of the joint system. And this tells you that system and environment could be in any state that belongs to this set. So now there are a few definitions here. So you say that this set is preparable if and only if there exists an input system R that you can imagine as being the pump, sort of, you know, like some kind of raw resource that you put into some box, okay, which is a completely positive linear map that outputs states in this set, all right? And the notion of preparability seems to be quite natural, no? Because how would you deal with a situation that is not preparable in the laboratory? If that is not preparable, then you might even argue that it doesn't make sense to think about such a situation. So let's start from the assumption that the set of initial correlations is preparable in this sense. Okay, so that there is a pump system, a raw resource system R, that when it's filtered through this completely positive map P, gives you states in SQE. And of course, for each state in SQE, there exists a state of the pump that gives rise to that state with a non-zero probability. Perhaps easier to understand is that is an equivalent formulation of preparability, which is in terms of steerability. So it is possible to prove a very simple result that tells you that the set of initial condition is preparable if and only if it is steerable. That is to say, if and only if there exists a reference system now. It's not a pump system anymore, but it's a reference system that is sitting somewhere else in the universe. And the tripartite density operator shared between reference, system, and environment, such that any state in this set can actually be steered. You see that here I perform a local measurement on R. This is a local effect acting on R on the reference. And then just by discarding R, it means that this effect is steering the state on the system and the environment. The condition of being preparable is equivalent to the condition of being steerable. And this forms a very powerful, mathematical framework to deal with the problem of initial correlations. The reason for this is due to the following result. So first of all, again, a little bit of nomenclature. I'm sorry, there are a few definitions, but I mean, my talk is meant to be theoretical, so I do this without feeling guilty or too guilty. So again, the set of initial correlations is said to be CPTP reducible if and only if for any interaction between system and environment together, there exists a quantum channel, so a CPTP linear map E from the system Q to the system Q prime alone, so like an open quantum system evolution, such that this holds. So it means that whenever you start from a joint system of the joint state of system and environment, you let it evolve according to the unitary evolution, and then you discard the environment, is equivalent to discarding the environment first and then applying the channel. Of course, the same channel should work for all states in the initial set of possible correlated states between system and environment. And then you have this result, which starts preparing the framework for what follows. So suppose that you have an initial system environment conditions that is given by a set that is preparable or steerable, equivalent. Then the following two statements are equivalent. So this set SQE is CPTP reducible. That is to say, for any joint interaction, there exists a quantum channel that describes the reduced system evolution. And the other condition is that this set is steerable from a Markov tripartite state. That is to say that there exists a tripartite state omega, which is able to steer the set of initial conditions, and at the same time satisfies the Markov condition, in the sense that the environment and the reference are independent given the state of the system. All right. So then the most simple situation, the situation of no correlation, this is the textbook situation. Of course, this falls within the framework of preparable initial conditions. You define this set as the set where sigma E is fixed, okay? So the state of the environment is fixed, whereas rho Q is free to vary through all possible density operators of the system. So in this case, a tripartite state that allows you to steer all these states is given by this, okay? So you have maximally entangled state between reference and system, and then you have a state of the environment which is tensor product form with it. This, of course, is in Markov's condition. Actually, you don't even have to condition on Q. Reference and environment are factorized, and therefore it is CPTP reduced. Very easy. Next step. So let's consider the counterexample that was provided by Rodriguez, Rosario, Cavanmodi, Sudarshan, and collaborators in 2008. So there, what they construct is the following set of states. So they fixed n environment states. All right, these are fixed. And the set of possible initial conditions is given by this polytope, where you have the state of the environment here, and then you have these orthogonal flag states, these orthogonal states on the system Q. And what varies here, what can vary as a free parameter, are these probabilities, PIs. So you have states of this form. They are correlated, of course, between system and environment. But what they proved here in 2008 by directly computing the dynamic matrix and proving that that matrix is positive semi-definite. So it's a rather complicated calculation. But if you look upon this counterexample from the viewpoint of steerable initial conditions, you see that this set of states, again, is steerable just by considering a tripartite state of this form, right? So you can have classical correlations between these three systems, and by performing measurements on R, you can induce any probability distribution here, right? Moreover, this tripartite state, it's easy, easily verified fact that it satisfies the Markov condition, and therefore, again, it is CPTP reducible. Is there more to this? So Shabani and Lidar in 2009, as I told you, they claimed that no, there is nothing more besides this example. And the reason for this is that they had a theorem that would say that CPTP reducible correlations would be all and only those that have zero discord. And this indeed is a state with zero discord. There are only classical correlations and between Q and E, and the system Q is classical in this sense. So according to Shabani and Lidar paper, there could not be anything more to this counterexample. But in 2013, as I told you before, there were counterexamples to this claim, provided explicit again by Broduch and again, I think, Rodriguez Rosario, Cavanmodi, and also probably Sudarshan is also among the co-authors. So the counterexample that they have here, a counterexample to this classicality of correlation, is constructed as follows. You had three distinct environment states, sigma 0, sigma 1, and sigma 2. And then you construct two states as follows. So one state is alpha QE, which is a mixture of these things, where you have a 0 here and you have a plus state here. And then you have another state, BQE, which is with 2. Okay, so this Q system is three-dimensional. You have 0, 1, and 2. And these two states are divided in this way. And the state of initial correlation is just the convex mixture, all possible convex mixture between these two states. So now, because here in the alpha state you have both 0 and plus, you cannot say that the correlations between system and environment are purely classical anymore. This is a state with non-zero quantum discord using the nomenclature of discord. And yet they would prove again that anything that you would get, so even if system and environment would start in any of these states, which are convex mixtures, so anyway, states with non-zero discord, still the reduced dynamic of the system would exist, and would exist well-defined in the sense that it would exist as a CPTP quantum. Again, this example can be very simply described in the formalism of repairable families, just by constructing this state here. You see that the reference is just steering the possible convex combinations, and again, it is easy to check that the Markov condition is satisfied, and therefore, due to the result I showed you before, this family is CPTP reducible. But one can ask whether it is possible to go further. So there are more general examples here, in the sense that until now, all the counterexamples that we've seen to the initial factorization condition only involve separable correlation. For example, if you look here, this state, the state alpha and the state beta, have only separable correlation between system and environment. These are convex combination of tensor product states. So the natural question would be, can we have CPTP reducible entanglement? Okay, and yes, it is possible to have CPTP reducible entanglement, just because the Markov condition here is very flexible. There are a lot of states, tripartite states, that satisfy the Markov condition, and yet when you look at the states that you can steer on system and environment, these could be entangled states. Okay, so it is easy to construct a lot of counterexamples with very, very strong correlations between system and environment. So the point is not much about how strong these correlations are, but more about a kind of a trade-off between the strength of the correlations and the size of the possible initial state space of the system. Because the more system and environment are correlated, the less freedom you have in defining the initial state of the system. Vice versa, for example, if you require that the state of the system span the entire set of density matrices, then the only possibility to have a CPTP reduced dynamics is to fall back onto the factorization condition of the textbook. Okay. So there is this kind of a very fine balance between the strength of the correlation and the size of the set of states. So now the next question is, what happens when the set of possible initial correlated state is not CPTP reducible or is not Markov steerable? So what happens here? And here we have the problem of non-Markovianity. So how to define non-Markovianity? Because now in this situation, as we will see, we cannot say anymore that the state of the system at a later time is entirely and only function of the state at the system at previous time. There are some non-Markovian effects. And whereas this effect can be very clearly dealt with in the classical formalism, because you can have a joint distribution at all times, in the quantum theory, we have to be more careful, and we will see some ways to go around this problem. And also we will see that actually there are still things that we do not understand entirely about the problem of quantum Markovian. So if the Markov condition is satisfied, so if you have that the initial set of correlations can be steered from a Markov state, this is also equivalent to the condition that for all joint evolutions of system and environment, the mutual information between reference and system do not increase. So it goes down. The initial correlation between reference and system is greater or equal to the correlations at later times. In other words, the Markov condition, which is equivalent to CPTP reducibility, is equivalent to the validity of the data processing inequality locally. And this is because, well, there is just a simple chain of inequalities. Here you use the chain rule for mutual information. And because the joint evolution here is unitary, the mutual information is the same. And again, you use the chain rule of mutual information that gives you this. So by comparing the initial and the final point, you see that the data processing inequality is obeyed. So whenever your initial set of correlations is not CPTP reducible, so it does not satisfy the Markov condition, here you have a strictly greater than symbol, then it means that information revivals can occur. You can find yourself with more correlations between reference and system at a later time than what you started with at previous times. So an information revival amounts to a violation of locality, because you have something that is happening locally on the system, and yet this induces an increase of correlation with a space-like separated system like the reference. Okay? So being a violation of locality, it requires an explanation, it urges an explanation. And what does it mean to explain an information revival? Well, you can just think like when you explain a magic trick, in the sense that when you see a magician pulling out a rabbit from a hat, you can always assume that the rabbit was there all the time. It was just you not seeing the rabbit, so the rabbit was concealed, but it was there all the time. There's no magician that is able to summon a rabbit out of thin air, right? So exactly in the same way, you would like to see that these revivals of information come from things that were there already together with your system. It was just you that, you know, discarded those degrees of freedom in the first place. So what does it mean, formally speaking, to do, to have and to explain a revival? So suppose that you have a revival. This is joint work with Gangwar, Goswami, Badani, Pandit Mohan Das, and Bera. So suppose that you have a revival, all right? So you want to explain. So what does it mean to explain? So that you have to find other parts, other regions of the universe and add them to Q, okay? So bring them together with Q until the revival disappears, right? So by putting here other parts of the universe, you want to naturalize this inequality. So from strictly less, you want to go back to the usual and comfortable data processing inequality. But you have to do this in a way that satisfies causality, in the sense that you want to find an extension of your initial state between referent and system, and the unitary operator that takes QE to Q prime E prime, such that what you get after the unitary interaction is an extension of the state at later time. So everything basically has to be consistent with your assumption that the system is interacting with the environment. So essentially what it means that you can add to the system its causal past, okay? If you do that, you can always find an explanation. You can always find, in particular, let me use this term, a causal explanation, which means to say that, you know, you can always, and how do you find this causal explanation? Just by starting from noticing that the state of the reference is the same, then by Ullmann's theorem, you know that there exists a purification of the state of reference and system at time t0. You bring it this purifying system E and you call it E. This is going to be your environment. And there exists also a unitary transformation that brings you to a later time that respects the causality consistency, the causal consistency condition, and such that the mutual information does not change because it's unitary, right? So this is an explanation because you are back to the comfortable data processing inequality. In particular, here you have an equality, which is even better. The thing to notice is that a causal explanation exists, but it's not unique. Okay, you can have many different explanations. So you can say that there is a process that you observe that is your system, and then the explanation that you give is at the level of some epistemic explanation. So it might not be the actual mechanism that causes what you see, but it is an explanation. Okay? And a causal explanation is also known as information backflow, because you explain the revival of information by imagining that some information has flowed from this environment back into the system. All right? So the information that you see in the system is due to some kind of yeah, to a flow that brings these correlations to the system again. So what we know now is that any information revival can be explained as an information backflow. But is a backflow always necessary, right? And I would argue that this is not the case. And the motivating example is constructed as follows. So let's start with a reference system and a system Q that are both qubits. And this is your initial state. So they are factorized maximally mixed states. But at a later time, they become maximally entangled. This is a blatant violation of data processing inequality, okay? So how can you explain that? Well, you can explain that, for example, by a causal explanation. So you can imagine that there is an environment here which is maximally entangled with the reference, and then the interaction between system and environment is just a swap operation that swaps the system and the environment, so that you start from a situation where referent and system are factorized, but then because the swap is swapping this entanglement from environment to the system, at a later time, system and reference are maximally entangled. And this is a backflow. This is a backflow of maximal entanglement from the environment to the system. But this is not the only explanation that we can give in this situation. There is also an alternative explanation, which would be the following. So here you see that you have now 4 systems. So you're doing something a little bit more interesting. So you have that the state of between references is given by the maximally entangled state, but the system is rotated with Pauli matrices in a random way, okay? Oh, there is 1/4. I forgot to put 1/4 here in front of the state. It's not normalized. But these Pauli matrices are perfectly correlated with the environment, which is in turn perfectly correlated with this other system F. And then what would be the evolution that brings you to this maximal entangled situation between reference and system? It would be just a controlled unitary. So this controlled unitary reads the state of the environment and undoes the Pauli operation on the system. So it cancels this out. But you see that now environment doesn't change and remains maximally correlated with F. And F never interacted with the system. And yet, you are able to explain this revival of information. So you were able to explain this revival of information without the need of invoking a direct causal backflow of information from the environment to the system. You could explain this revival just by looking at F, which never interacts with the system directly, and therefore it could reside in a causally separated region of space-time. So this brings me to introduce the notion of non-causal explanations, which contrast with the notion of causal explanation, the notion of a backflow of information that we had before. So again, consider a revival, right? So you have a violation of locality at the level of the reduced system dynamics, a violation of Markovianity. So if there exists an extension, a 4-part type in this case extension, and a unitary that takes Q and E into Q prime and E prime. So F is left aside. F never interacts with this. It's outside the interacting area of the universe. And this extension with the unitary gives you an extension of the state at later time, sorry. And it's able to explain the revival that you observe. So it's able to naturalize this violation of locality and bringing it back into the range of validity of the data processing inequality, we see that revival is non-causal. And why non-causal? Because, as I said before, the extension F that you use to explain the revival, so this part of the universe that you bring together with Q to explain the revival that you are observing, never interacts with the system. And it may reside in a causally separated region of the universe outside the causal past of the system. So now the question is, so sometimes you have backflows that can be explained by using a non-causal explanation. So are there situations instead where in order to explain a revival, you really need a backflow? There is no other option for you but invoking a causal backflow of information from the environment to the system. And here is a sufficient condition for the existence of a causal backflow to suppose that there is a revival. So now, a causal explanation is the only possible explanation if and only if, this is a tautology, if and only if there exists no non-causal extensions, right? So for all F, everything that you do, however you try to extend your system, you will always have this violation of locality. So in this case, a causal explanation is the only one that works because we know that the causal explanation always exists. So now a sufficient condition for the above is that, you can just, take the conditional here. It's just, you just rewrite this in terms of the conditional mutual information, and then you take the supremum here, and you ask that the supremum, however you look here from the viewpoint of this extension, and take the supremum, is always going to be strictly less than the infimum that you can do at the later time. And a sufficient condition for this is that, for example, the entropy of the system at time t0 is strictly less than the entanglement between reference system and later time. This is the squashed entanglement. So, for example, a situation where only a causal backflow of information can explain the revival of information that you're observing would be the following, where reference and system start in a factorized state, but with a pure state for the system, and at a later time, you see that reference and system are maximally entangled. In such a situation, there is nothing that works but a backflow of information from the causal path of Q to Q prime. There is nothing else that can work. Okay? So you need a direct causal backflow to explain what you see in this situation. So now let us go back to the problem of initial system environment correlation, where the set of possible initial conditions is steerable, so that we can use this tripartite formalism, which is very handy. Okay. So if we can find an extension of this tripartite state, such that the mutual information between R and E given Q and F together is 0, then for any unitary interaction between Q and E, the data processing inequality is obeyed, is satisfied if you bring F together with Q. So it means that if your tripartite state, the state that you use to steer this initial condition, is can be extended with an extension that satisfies this condition, you might observe revivals, but such revivals will never be causal. You will always be able to find a non-causal explanation for the revival, right? So this suggests that, the separation that you typically find in the literature between Markovian process and non-Markovian process, so processes that for which the instantaneous information about your system is all you need in order to predict the future of the system. This is the Markovianity condition. And instead, situation where that is not enough. So a situation in which you have revivals of information, okay? Or when your evolution is non-divisible, right? So the separation between these two cases is not enough somehow. I mean, if we were only to look upon Markovian versus non-Markovian, we would be missing something from the picture that is the role of the causality of the explanation. So what this suggests is that we should be able to, or we should actually look more into a hierarchy of possibilities. So that starts from the case of no correlation at all between the reference and the environment. This is the textbook case. And then you have the next step, which are correlations, so possible correlations between system and environment, but correlations that satisfy the Markovianity condition. So system correlations that are there, but don't cause any revival whatsoever. So the Markovianity condition is always satisfied. And then the next step instead would be to see for non-causal correlations, so correlations that are there, correlations that can cause revivals, but revivals that do not require a causal backflow in order to be explained. So you have this hierarchy of possibilities that mimic somehow the separation that you have in entanglement between space-time separated regions. You have total correlations, you have genuinely quantum correlations that you use entanglement, in order to quantify such genuinely quantum correlations, and then you have what is left out, which you can call, for example, classical correlation. So let me skip this part and let me go to the conclusion. So I would like to say that essentially there is an entire new area that I hope more people will start looking into, which is really the role of time-like correlations in open quantum system dynamics. Time-like correlations that can be understood really in terms of entanglement in time, which would be, correlations that cause revivals that are that require a backflow, causal backflow to be explained. So this would be the genuinely quantum non-Markovianity. Yes, here. So, and instead revivals that can be explained with a non-causal explanation. So like I would say kind of boring revivals or non-genuine revivals, okay? We have a condition for the genuine backflow. And then, okay, if you want, yes, this is the slide I skipped before because I'm late now on my timetable. But you can also consider these things from the viewpoint of a resource theory of Markovianity. So we need to understand more about time-like correlations. A lot has been done, but I think that still a lot can be done. And there are various viewpoints that are getting clearer recently. And I hope that this will attract more and more interest from the community. I thank you very much for your attention.
Thank you, Francesco. So in this session, the plan is like we will have our speakers, the talks one after another, and then we'll have a coffee break, half an hour. After that, a discussion session will start. So for now, we will please stay online so that you can hear Ashok.
Yes.
So Ashok will be the next, and after that we'll have half an hour coffee break, and we'll take all the questions after that. Okay. So Francesco, thank you very much. Thank you. Please thank him. Yes.
Thank you very much for your attention.
Yes. Thank you so much. Our next speaker is Professor Ashok Ajoy. So Ashok did his PhD from MIT, and then he was a postdoctoral fellow in University of California, Berkeley, where he joined as a faculty member. So Ashok does experiment on open quantum systems, and particularly using NMR as the model. So he works on various fields, NMR spectroscopy as well as quantum thermodynamics. In a way, he looks at the thermalization and pre-thermalization problem using experimental avenues. So he will give us an overview of recent developments in this field. Ashok, over to you.
Okay.
Yes, I will.
I think it's yeah. Okay, great. Yeah, I got it. Okay, great. Well, it's great to be here. It's actually my second time in Calcutta. Last time I came, it was the summer and it was so hot, and It's great to be here, and unlike the previous talk, I should give a lot of kudos to Francesco. I guess I'm not going to have any equations because I'm experimentalist. I'm going to show you a lot of figures and wave my hands about how the experiments are done. So we are indeed looking at open quantum systems, systems that are far from equilibrium, that we excite in spins. These are electrons or nuclear spins. But then I'll show you about frontiers of what one can achieve with these sort of systems. Okay, and I'm representing UC Berkeley and Lawrence Berkeley National Lab in California. So, so what I'm going to tell you today is how we can exploit far from equilibrium systems. Okay, so really these are systems, and mostly I'm going to talk about spins. So these spins are going to be very far from equilibrium, and as an experimentalist, you care about, for example, attracting funding, attracting students. So you want to tell them why is it useful, apart from it being interesting. And it's useful because we can actually construct what I would call quantum sensors. So you can actually sense things very sensitively with these far from equilibrium systems, as well as sort of explore a wealth of physical phenomena that I'll tell you about. Okay, so the work I'm going to show you today is largely on these particles and crystals of diamond. You're going to ask me, why is diamond interesting? And this is actually a picture with my iPhone. So this is how these particles look. We buy it from De Beers, and it's actually surprisingly very low cost. Okay, so a gram is about a few cents. Inside these materials, inside this material, diamond, diamond is pure carbon, and you have C13, which is a nuclear spin of carbon that comes with 1% natural abundance. So you have carbon-13 as a nuclear spin. We also dope the sample with these NV centers. I'm not going to talk about it. I think someone mentioned it in the morning session. So you can just think of them as crystalline defects that you put inside the lattice. And these are electrons, and these are nuclear spins. So this is going to be like the foundation system over which I'm going to describe how you can do sort of non-equilibrium physics with these systems. Okay, so some advantages are it's a room temperature system, and it's truly an open quantum system, as I'll describe in a moment. Okay, and I should say that I'd love it to be interactive, although there's going to be discussion later, so you can always stop me if something's not clear. In particular today, I'm going to tell you a lot about nuclear spins. So these are very ubiquitous. They come with, in all matter is made of atoms, and a large proportion of the atoms have nuclei with spin. And in this case, in diamond, the spin is carbon-13, so C13, and it's a classic spin-half nucleus. So very simple. It's like textbook spin-half physics. But some things about it are, it's very easy to control these spins. As I'll show you, we are applying something like 1 to 10 million pulses on these spins. Okay, so as an experimentalist, you can ask how well can you control a quantum system from the outside. This is governed a lot by what kind of control you can bring to bear on the system. And here we can bring to bear a tremendous amount of pulses. They also have very long lifetimes. So we use these metrics called T1 and T2. T1 is the time for which a spin prepared in a particular state will live there, and this is about an hour in our case at room temperature, so very long. And also very long coherence time, or T2, which I'll describe in a moment. These spins are also very abundant, and they are strongly coupled, so you can think of it like a quantum interacting many-body system. All these nuclei are interacting with each other with a dipole-dipole interaction. So the dominant type of interaction is a magnetic interaction. And really exquisite control is possible. Okay? And I'll skip the details because it's not so important for this talk. That it's actually possible. Usually these nuclear spins are very hard to work with because they're very long T1s, and their purity, state purity, is actually very poor. So in our community, we call purity as polarization. It's just another way of saying the same thing. So 100% polarized spin will be a spin in a pure state. And the polarization is very poor, and we actually boost in our experiments, we boost the polarization with laser excitation. And I'm just going to skip this whole topic and just give you the final result. So what we do is we take the electron, which is this NV center, we blast the diamond with light, and it so happens that you can actually boost the polarization of the nuclear spins quite significantly. I'll show you what the result looks like. If I can get that to work. So typical experiment, if you do, the readout is through a technique called NMR, which also I won't describe. You can just imagine it as reading out the spins through a RF cavity. And typically the experiment after 8 hours of averaging would look like a signal to noise or so, very poor signal to noise, and you zap the laser for a few tens of seconds and you can get a signal to noise like that. So it really tremendously boosts the signal, and you can calculate various things, but the experimental acceleration is between 8 and 10 orders of magnitude. Okay, so really huge signal and very little laser power required. Just shine a laser on the sample, and suddenly now these nuclear spins, which have these very long lifetimes, very long coherence times, as I'll describe, now suddenly become accessible to you because you can measure them very efficiently. Okay, and that's kind of what I'm going to tell you about. Okay, but you know, as for the purposes of this conference, I wanted to say that this is a really classic open quantum system. It's a very dirty environment these spins are embedded in. Okay, there's some diagram, but I'm not going to go through it. But you can just imagine that here you have nuclear spins, you have electrons, you have different types of electrons, you have strain in the lattice, you have you know, various other kinds of dangling bonds, and basically just junk, noise. And this is very typical of any quantum information system currently. So almost all experimental quantum processors, either they're superconducting Josephson junctions or ion traps, all have, you know, versions of the same kind of noise that we encounter in our system. And so it is truly an open quantum system that way. But the advantage here is that we can apply a large number of control pulses on these systems and be able to probe a thermalization phenomena over very long periods of time that are, I would say, inaccessible in other systems. Okay, so that's what I'm going to tell you about today. So what I thought I'll tell you about is 3 topics of current interest. One which is called pre-thermalization, as Rangit pointed out, how you can actually put spins into a state that lives long but is far from equilibrium. And then a manifestation of that is what are called time crystals, and I'll tell you a little bit about that. And then I'll tell you about how you can make right patterns like this in spins, so you can write a onion shell of polarization, spins up and spins down, and keep that alive for tens of minutes. And finally, what I want to come back to towards the end is, because I'm an experimentalist, we care a lot about doing things that are of practical utility to other people. And I'm going to tell you all of this gymnastics is on spins, but these spins can then be applied to the real world. So towards the end, I'm going to show you how we can deploy these spins into various platforms of practical utility and do interesting things with it that are practically useful. Okay, and that's how I'm going to end. So I'm going to tell you about these pre-thermal nuclear spins and how you can make sensors out of them. By the way, this is all experimental data, so I'm going to show you that. So the first thing I wanted to start off with saying is, if you were to look at the nuclear spins and just do a simple experiment, which would be, you know, in our parlance, what's called a free induction decay. That's a pi-half pulse followed by a measurement, which is you tip the spins on the equator of the Bloch sphere, and you're measuring them. And you'll notice that the spin coherence dies pretty fast. So, you know, it's about a millisecond or so. And this millisecond occurs because these spins are actually strongly interacting with each other through this Hamiltonian, which, you know, if you're not so theoretically inclined, can look rather complicated. This is a magnetic dipole-dipole interaction. It's an all-to-all interaction. And all the spins talk to each other. And there's a weighting factor, which is 1 over r cubed. And then there's some, you know, polymatrix terms here. It's got some angle dependence as well. So, you know, it can look rather complicated. And you have this Hamiltonian that's always acting. So there's no easy way to turn it off. And this sort of leads to this decay. And, you know, in different communities, a millisecond can be respectable by itself. But, you know, it's, as I'll show you, it's a very lousy coherence time that the spins can have. And this short coherence is a challenge for many experimental things of practical utility. Like, say you want to make a sensor out of it. If you can only measure the sensing signal for 1 millisecond or 2 milliseconds, it's kind of fairly practically useless. So, so the main result I wanted to show you today is that we can do some things to be able to improve this lifetime. And one simple thing is to, I'm going to show you the result first and then tell you what we did here. But in this experiment, something was done to go from here on the left panel to here on the right panel, and you'll note that the axes have changed quite dramatically. So you've gone from tens of milliseconds on this axis to hundreds of seconds on this axis. And suddenly now the lifetime, if you were to just consider the lifetime as a 1 over E crossing, the lifetime has increased quite significantly, a factor of 60,000 or so, right? So it's suddenly reached a T2 time, T2, what I call T2 prime for experts, but of about 90 seconds. And what was done in this experiment was a train of pulses was applied to these spins, okay? And we'll describe how this works in a moment. But what we're doing very easily is just a train of pulses, and we're measuring the spins in the windows between these pulses. So each little window here produces 1 point on this graph. And in this experiment, there are 6 million pulses. And so there are 6 million points on this graph. And you can measure this continuously all the way to close to 10 minutes. So really, suddenly now you've got this dramatic improvement in lifetime. And at first sight, this was rather surprising, but now there's a very easy way to explain this. And the simple-minded experimentalist explanation of this is as follows. What you're doing is you're taking this dipole Hamiltonian that I wrote down in the previous slide, which is rather complicated, and you're re-engineering it into something else. So there is some new Hamiltonian now, such that the initial state commutes with this new Hamiltonian to some order of a series expansion. The series expansion is often called the Magnus expansion for experts. And what you're doing through this, some order of this series expansion, you have the state that's thermalizing into this Hamiltonian. So it's not a true thermalization because it's only approximate to some order of some power series. But you can imagine that to this approximation, you have the system behaving as if it was following this graph here. So if you plot the same data on a log scale, it would look something similar to this, where the system relaxes fast and then would sort of fall into this plateau region, which is also called the pre-thermal plateau. So it goes and sits in this sort of metastable state where it will live for a very long time, after which ultimately it would decay and reach the true thermal equilibrium, which is a fully mixed state. Okay? So you can sort of arrest thermalization by putting the spins into this plateau region, and this plateau can be very long. And during this plateau, you can measure these spins and you can manipulate them continuously. And this is a very interesting thing because the plateau can be, as we're seeing here, tens of seconds. Yes?
Just a quick question. Is this creating a decoherence-free subspace?
The mechanism of operation is different from a decoherence-free subspace, but you can imagine that to a philosophical extent, it's still also arresting thermalization. We can talk more about why maybe in the discussion. But a simple-minded explanation is you're forming a new Gibbs ensemble, if you like. You're thermalizing to this new Hamiltonian, but this Hamiltonian is only approximate, and therefore this equation only holds approximate. Yes? You had a question? Yes? Okay. Well, okay. It's not a Hahn echo, so I'll describe why. So the theta is not a pi, but it's some other angle, and it won't work for theta equal to pi. Okay, but this is a technical detail. But the thing I want to leave you with is you can measure this. Not only is the time extended, but you also have, like on this graph, now suddenly 6 million points. So you can really observe these spins for a very long time. Okay, and I know I'm going to skip this section, but there are some interesting things you can do with it. A lot of people, who are my colleagues in quantum information, they would report T2 or T1 as a 1 over E crossing. So you would take a data that looks like this, and you would just literally plot a intercept, and you would say, oh, that intercept is 106 seconds, so my T2 is 106 seconds. So this is a good proxy if your graph was a mono-exponential, but you know that most of these decays are not mono-exponentials. But the advantage we have is we have like 8 million points on this graph. So instead of just taking the 1 point that intersects with the 1 over E, which looks like a very poor proxy, you can get all the information that resides in this 8 million points. And you can do something called a Laplace transform instead of Fourier transform and decompose this curve into its constituent mono-exponential. So if you do that, you get a curve that looks like so. So very high resolution spectroscopy of the noise processes that the spin encounters here. And we will skip the details of what this means, but the point to note is there's like 5 orders of magnitude in time here, and these spins are encountering different relaxation channels that span these orders of magnitude in relaxation rate. But armed with this knowledge, we can go and, first I want to share, before I go there, I want to say that this Laplace business is really excellent. As an experimentalist, when we do curve fitting, we always ask, like, how good is this curve fitting? Like, how do I know that this is actually an accurate reflection of this? And the way to do this is to take the data and fit the data and look at the residuals. So that's what's shown here. The data and the fit are overlapped very well. And if you look at the residuals, there's less than 1% variance over 8 million points. So, this is a really good fit, and therefore we know that this way of representing this data is actually an accurate sort of reflection. And then each of these peaks, because they're separated by some orders of magnitude, are different relaxation mechanisms altogether. Okay, so this is like you can think of it as noise spectroscopy of these qubits. Okay, anyway, armed with this knowledge, it turns out that we can go better. So in newer work, we went from something like 100 seconds to something like 500 seconds by, since you know something about what the system is seeing, you can be more clever about pulse sequences that you can apply. And then I'm going to skip how we did this. You can ask me in the discussion. And in the most recent experiment, we have been able to reach a lifetime of this T2 prime of 800 seconds. So we've gone from normally 1.5 milliseconds to 800 seconds. This corresponds to an improvement in lifetime of 500,000, okay, just with some pulse sequence. And in this case, we are applying 7 million pulses. That's 300 seconds on this axis here. That's 5 minutes. And you can see that this top curve is hardly decayed to much over 5 minutes. Okay, so really, this is like the nuclear spins are undergoing Larmor oscillations for experts, and during this period it undergoes something like 10 to the power of 11 Larmor oscillations, and you're able to track the spins continuously over this long period. Now suddenly, this is very interesting because not only can you keep the spins alive for a long time, you can watch them continuously, and now you can play games with these spins. So I'm going to show you what kinds of things you can do with this canvas that we set up. Okay. So one easy thing you can do is to make a sensor. Okay, and I'm going to skip the details of how it works and just tell you a very simple principle and show you data of how it's working. So in the previous experiment, we had a train of pulses. You can imagine the spins were locked along a particular axis. So they lived long along a particular axis. So we would call this spin locking, just like old jargon, but it's locked around an axis. Now you can ask, what happens if the spins were exposed to a weak magnetic field? Something like so, okay? And a classic quantum sensor is such that is trying to detect a very weak magnetic field, like a time-varying magnetic field, like a few nanotesla in size. So if the spins were exposed to a weak magnetic field, you can show that what would happen is that the spins that were formerly locked along a particular axis now start to wobble around this axis. Okay, and this is very interesting because now suddenly this pre-thermal state that we assumed was time-independent, like locked in a particular direction, now becomes time-dependent, but will still retain its property of being long-lived. Okay, very interesting why that happens. But anyway, so suffice to say that whatever this field is applied, you would get a direct imprint of this field in your measured signal. So while previously your signal was a flat, kind of very boring decay that lived very long, now suddenly you can see your signal in that signal. Okay, and here's data that shows this, and I'll skip the details of how this is done, but I just want to say that this is data measured continuously for 10 minutes. We're exposing the spins to a weak magnetic field, maybe a few microtesla here. And what's shown is the measured signal as before, but in different windows. So at 1 minute, 3 minute, 5 minute, 10 minutes. And you'll note that these spins are wobbling for 10 minutes continuously. Okay? And so it's very interesting that you can take this pre-thermal state that's metastable, far from equilibrium, but still sort of arrested from thermalization. And now you can endow it a property that it becomes time-dependent, and this time-dependence now reports on some field. So you can literally do this experiment like sing on top of the spins, and you can watch your voice on it. So you can make an audio receiver. Okay. Yes.
So the magnitude of those thing will decay, will have a long time.
Correct. Yes. Yes. With the same decay time constant. So you'll note that towards the end here, the signal to noise is worse. That's what's shown here. It says SNR of 15, SNR of 58. Yeah. Mm-hmm. Indeed. Yeah. Right. Okay, and I'll skip the details. For experts, we really care about doing things of practical utility, and well, you can draw all these plots showing how good is the sensor with respect to sensitivity and operation conditions, etc. And it turns out the sensor is pretty good, and I can talk about it more in discussion. I think for this audience, that maybe it's not so interesting. Just I wanted to say that this is a practically useful sensor and operates in a regime that most other sensors do not operate. But let me show you now some interesting things you can do with these spins now using this ingredient that, hey, not only can you lock them along an axis, you can move them away from an axis and still preserve their long lifetime. Okay? So the simple experiment you can do is similar to what I just showed you, but let's consider a variant of this experiment. Now what we're going to do is apply a train of pi-half pulses, so 90-degree pulses. All the pulses are 90 degrees, and we're going to apply a field such that you complete one period of this field after 4 pulses. Okay, so you can imagine now there's some symmetry built into this whole thing because it's a 4-point periodic. After 4 pulses, you've kind of got back the same situation that you have on this diagram here. So it's like a building block that repeats, ad infinitum. In this case, maybe 10 million pulses, and then you would this wobbling dynamics now looks as if the spins are sampling the corners of a square, okay? And this is real data. This is what I'm going to show you. But you can actually watch the spins in real time. You can think of this like a weak measurement. And we're watching the spins in real time, and you can see the spins capture the corners of a square. So one easy way to visualize this is to look at the YZ projection of the spins and plot them as a function of time. So that's what's shown here. So this is YZ on the block sphere, and time on the vertical axis. And this is no data processing, no hocus pocus tricks. This is just like raw data plotted in this fashion. And you'll see that the spins undergo this very symmetric prism-like motion, okay, which reflects that literally, you can make these spins move in this shape that looks like a square and keep them stable for, multiple seconds. Turns out you can do this for 100 seconds as before. And you can play all kinds of games now. You can make a screw. You can make a star. I think I put a star. Maybe next, yeah, so star. So my students have a lot of fun with the games that you can play with these spins. And this is the most recent incarnation. So this is a Golden Gate Bridge, where we are from in Berkeley. Overlooking the Golden Gate Bridge, and this is time on this axis. So there are all these shapes you can make, but you can ask, like, what are you getting at? What's the big deal that you can do this? The big deal I want to take away is the following: you have these spins; they're strongly coupled, they're interacting with each other. It's a quantum many-body system. It's a 1/r³ all-to-all interaction, and the interactions are not turned off. We're not doing anything to turn off the interactions in this case. And normally, if you don't do anything, the spins will die very fast. But now we're doing some pulse sequence. Not only are we keeping the spins alive for a long time, but we are able to move them around the block sphere in complicated dynamic trajectories that live for tens of seconds and millions of pulses. The main message is all of this works because of the interactions between the spins. So the interactions are a stabilization force that stabilize the motion of the spins and keeps them alive for a long time. Okay? So this is pre-thermalization, but not along one axis. So the one axis case is like the most trivial, boring thing. So what if you keep the spins alive around one axis? So what's the big deal? But here you can do more interesting things with it, but retain the same physics. And so I want to tell you about how this works, again, from a very simple experimentalist perspective. How do you understand this experiment? And this simple experiment describes this. So what we've done in this case is dynamically change this field that the spins are exposed to. So you have the spins starting locked along an axis. And as usual, we are tracking the motion of the spins in real time. So this is the YZ projection. This is time on this axis here. So you track them, and they're locked along an axis. Well, YZ projection is a point. This point then becomes a line if you stretch it in time. And then at some time, 1 second after the motion, the spins are asked to move in a motion that looks like a square, okay, as before. And you'll note that for a short amount of time, it's almost like the spins don't know what to do, after which they will thermalize into this long-lived state. And this is real data, so there's no processing. They live like this for as long as you want, hundreds of seconds if you'd like. And then when you turn off this, they go back into this square. Okay? And so the simple-minded explanation of this is, as before, what we're doing is we're re-engineering a Hamiltonian. The Hamiltonian is now time-dependent. The K here, index K, is supposed to mean like, in this case, there's a 4-point periodic motion, so you can imagine there are like K index spans from 1 to 4. There are 4 types of Hamiltonians. And this is a complicated dipole-dipole interaction modified with the pulse sequence, etc. But what happens once again is the spins are thermalizing to this Hamiltonian to some order of a Magnus expansion. And because of this time-dependent thermalization process, you once again get a pre-thermal state, but this pre-thermal state is effectively, apparently time-dependent. And you can maintain this long-lived state for a very long time. This has given rise to many interesting things that we can do with this suddenly. Now this new system that we have, we can play lots of interesting tricks with it and games with it. But this is the fundamental physics of what's happening here. So I want to show you some things we can do with it. So some things we can do is to make very interesting new types of sensors. So if you're aware about how spin sensors work, there's a classic Ramsey measurement of spin sensing, which I'm not going to go into details of. But you can imagine what you can do is, I'm going to drive the spins into a motion that looks like a square. And now suppose a perturbation is applied to the spin. So the spins see a perturbation. I know that my square, formally a square, would be deformed in some very specific way, but I know that this deformation will be symmetric because I've got some corners of the square. So if I've got some noise source that's not deforming it in a symmetric manner, then I know that it's something else that I can cancel, etc. So new types of ways by which we can do sensing, and I'm going to skip the details, but here you can show here that this is a field deformation that's applied, and you can track any of the corners here, and you'll note that the corners have the same imprint that I showed you now, except you didn't have one imprint. Now you have 4 imprints. The spins are like dancing around, but the 4 imprints are exactly shifted by 90 degrees, and you can use this property to help you to suppress noise. Okay, and I'll skip the details, but this ability to use new types of long-lived states for sensing is a very interesting concept. And also here we are exploiting the interactions between the spins. So the normal notion is that interactions are very bad. You should try to remove interactions between all quantum objects because interactions can kill you. On the contrary here, the interactions help you. They give you the stabilizing force, and they allow you to do all these interesting new tricks that you can exploit to make better sensors. Okay, so with this, I will stop talking about that and move on in the next 5 minutes to tell you a new variant of this, which is you can make so-called time crystals using the same concept. Once again, I'm an experimentalist, so I'm going to give you a very high-level explanation of what a time crystal is. I'm sure many of you have better ways to articulate it. But as an experimentalist, what I find interesting is as follows. So let's consider the same experiment as before. We have a train of pulses. The spins are locked along an axis. Already, this behooves a very interesting and simple question. We're applying 6 million pulses. Some of the experiments I showed you are 10 million pulses. So obviously, these pulses have error, like every other quantum system. Pulses maybe have 1% error. So why is the error not contributing to decay? And what happens to the error? Okay, so hold that thought. But what you can do is you can artificially sort of ask this question in a different way. So what's done in this experiment is every so often we kick the spins away from this axis. So we try to make the spins go from x into minus x with a pulse that's gamma along y. Okay, you just imagine that you're applying something like a pi pulse that moves the spins from x to minus x. So you're like tipping them from x into minus x. The classic thought that you would most obviously think is, suppose this pulse had error in it, like every other pulse has, but let's artificially inject error into this pulse. You would imagine that this pulse was not pi, but actually pi plus epsilon. So you had an over-rotation or under-rotation by epsilon. Then the more of these you do, the worse you'd get. So sometimes you would over-rotate to epsilon, and then maybe the second time to 2 epsilon and 3 epsilon, etc. And very rapidly you would decay. Okay, and this is very classic. It's actually all people doing any types of quantum information processing. The first thing they would do is calibrate all their pulses with pulse sequences that look like this, which magnify error, and you would try to remove the error by calibrating these pulses. And the interesting thing about these time crystals, or these time crystalline states, is that they are robust against errors to this pulse. So you can have a large amount of error, actually, but this error will not matter. And the system would still automatically want to go from x into minus x. Okay? And as an experimentalist, I just find that very interesting. I can tell you why that works, but that's just a very interesting, practically useful thing. I mean, you can talk about all this period doubling and this and that and whatnot, but from a very simple practical standpoint, this idea of robustness to errors in a particular pulse is very interesting. So I'm going to show you that this works really well. So what we're going to do is run this experiment, but as I showed you, we can watch the spins in real time. So you can literally do this experiment and watch them, different angles of pi here, and you can see these, each of these steps is the application of this pulse, this error-full pulse. And now you can imagine that there's a large amount of error in this pulse and the spins have completely died. But the very interesting thing happens is the pulse approaches gamma equal to pi. So as the spins approach gamma equal to pi, you'll note that you get this sort of pattern of x minus x, x minus x, and this would remain stable for a very long time. Okay? So this is the data that shows this. We can run this in one shot, unlike most other experimental apparati. And you can see that what you're showing here is x and minus x, and the pulses have 3% error. But although they have 3% error, you can apply hundreds of pulses and still maintain very high stability. If you were to zoom into one of these windows here, this is what it would look like. So really, it's hardly decaying at all, and you can see x minus x, x minus x. This is like data, not simulation. And you don't have to do this in a periodic fashion. You can do it in any fashion that you like. So you can make a quasi-crystal if you wanted to, whatever, right? So it's not important like what periodicity you apply these things to, but you can still have them stably bouncing back between two rails, and this can be very stable in a manner that is robust to error. Okay, but you can ask, why does this happen? And the answer to why this happens is best seen by actually plotting the phase diagram of this time crystal. And because we can run these experiments very fast, we can map the entire phase diagram experimentally. So this shows the phase diagram. This shows the angle gamma on this axis and the time or Floquet pulses, the number of these gamma pulses in this axis. And you'll see here that there's a huge stable point around pi and 0. So 0 is trivial because you're not doing anything. But you have this high point of stability around pi. And if you plot on a log, so you can see here you have this striped phase that appears. And the striped phase, really the spin's flipping between x minus x, x minus x. If you plot this on a log scale, it'll be clearer. But you have this sort of dome of stability that shows up along this point here. And in my mind, this is the most interesting, useful thing about a time crystal, that really you can have error that you can artificially inject, which can be quite high. 3% error in any QIS platform would be basically useless. But here you can tolerate a large amount of error and still go, hundreds of pulses. Now I'm going to skip this because it's slightly more technically detailed, but it turns out you can do even more interesting things with it because if you come back to what practical utility does a time crystal have, it turns out you can make a very sensitive sensor with a time crystal. So we are going to do the same experiment that I showed you before, but we're going to now also apply an AC field along with this time crystal in state. So now we're adding complexity. Have a time crystal and you have this AC field, and this is the signal without the time crystal, so it's artificially made bad, okay, because you want to see the effect of the AC field. So it turns out if you do something, you get a fairly fast decay of this time crystal in state. This is x minus x, but it turns out if you apply this AC field, you can have the time crystal living longer. Okay, so you can have a resonant enhancement in the time crystal in lifetime, which can be over a factor of 10,000-fold. And it turns out that this extension is actually a resonant phenomenon, and so you can make a very sensitive sensor out of it. So, in this voice analogy that I was telling you, you can sing, but you can tune your time crystal to only pick up a particular frequency. Every other frequency is suppressed, and you only will have this one frequency that contributes to your signal. And why this happens, I won't have time to tell you about, but suffice to say that there is a new interesting types of sensors you can make with these time crystalline states that, so it's a kind of wealth of phenomena that can be explored. I'm going to skip this, and also I've got another plot that shows that this sensor actually is very good and it works in some regime of operation that no other sensor works very well in, so there's really some practical utility of this sensor. And I'm happy to tell you more about this towards the end. This sort of brings me to the end of, oh, sorry, I have I forgot, I have this one more story to tell you about. So I was telling you a lot about stability in time, but in 2 slides I'm going to tell you that you can also do the same kind of stabilization but in space. Okay, and it's also a very interesting sort of thought experiment you can run. So you can ask the very simple question. So you have this complicated dynamics of these spins. So, okay, so what if you can make these spins move around and make all these time crystals? Who cares? Maybe because you still have a large number of these spins, can you actually make a pattern like this and stabilize it in space rather than in time? Okay, and it turns out the same thing can be played even in space. So let me just first lay out the problem statement. The problem statement is to create a pattern that looks like this. Half the spins are polarized up and half the spins are polarized down. Okay. Now you can argue that that particular state is actually typically a very unstable state, because you have here a domain wall of polarization, a domain wall of spin pointing up and spin pointing down, and the spins are strongly coupled to each other. And so you would imagine that if you just let the system go from here, the system would completely melt. It's actually similar to opening a perfume bottle in a room. You would get diffusion of the state. Because why would the spins want to remain in the state? There's no reason for them to want to live in the state. And they would completely die very fast. And this state will not be stable. Actually, you can prove that it's very, very unstable. Anyway, it turns out that it's possible to create a stabilized state like this. And the idea is, following from what we were doing before, is to now create a Hamiltonian that has a spatial structure that looks as so. Okay, and it's possible to, with some tricks, to create a Hamiltonian that looks like this. So instead of creating the state that looks like this, we're going to create a Hamiltonian that looks like this. And then you could start with any state. If you were to start with any state, you could even start with all the spins polarized up. It would happen that then the spins will automatically thermalize into a shape that looks like this. Okay, so it's a very interesting sort of thought experiment, because it's like you could start with a bar being hot, as so here, and then the bar automatically thermalizes into half hot, half cold, because the Hamiltonian dictates that that is the new equilibrium state that it has to reach. So we've done this experiment. We show that it's possible to create this state. I'm not going to show you, I'm not going to have time to tell you how we did it, but the experiment is actually very simple. Someone asked, can you use a pi pulse train? It turns out the experiment is exactly a pi pulse train. And if you apply a pi pulse train, you can actually see the formation of these shells automatically. Here are some simulations that show this work in maybe a little bit more transparently. What's shown on this axis is time in some normalized units. What's shown on this axis is space in 1 dimension, so it's a 1-dimensional simulation of this experiment. You can start with all the spins polarized up. You can start with all the spins polarized up, and you just leave the system. And if you just leave the system, the spins will automatically sort of move in this along this time axis, and then suddenly the spins in this region flip automatically. Okay? And this domain wall is pinned, and this domain wall remains stable for a very long time. And so the idea is that by engineering Hamiltonians that have spatial structure and exploiting pre-thermalization, you can now create new exotic states of spin texture that can remain stable for many minutes as before, but now also have spatial structure. And that's what it looks like in 3 dimensions. Okay, so it really spans several nanometers, and it has, it encompasses tens of thousands of spins, and we're using this to create new types of molecular imaging, and that's the practical utility of this experiment. Okay, and since I'm almost out of time, I'm going to finally end by saying what I was saying before, which is all of this spin gymnastics is very fundamentally interesting, but really I feel like as experimentalists you also have to show practical utility. So why would you care about this? Where could it be useful? So it turns out because most of the experiments I showed you were at room temperature and can be done in nanoparticles of diamond, we're actually looking at the nuclear spin of carbon inside diamond. But the lattice shape of the diamond itself doesn't matter. Okay, it's just like lattice. And you can take the diamond and put it into different things. So a large part of my group is working on deploying these particles or sensors into new types of form factors. So I'm going to show you some examples. I don't have much time, but otherwise I could show you more. But some examples as follows. Here we are 3D printing diamond. And so this is a diamond boat. A diamond frit or a sponge of diamond. Each of the walls here have diamond inside it. So we create new types of 2-photon polymerization, 3D printing, and you can have the nanodiamond particles that take interesting shapes. So here is another example. This is a new type of manufacturing called bubble printing, but we write Cal. right, this picture from Michelangelo, etc. So the interesting things here are you can spatially structure the lattice in three-dimensional geometries, but the spins inside the lattice have all these very interesting time domain properties, and now you can exploit them both in parallel. So here are some examples. So I want to show you this 3D printing stuff really works well. So this is maybe not a very good projector, the screen, but this is a SEM picture of this 3D printed structure. And what we're doing here is confocal imaging. And this structure is what's called a gyroid. It actually is provably the largest surface area structure inside. They have these large pores. And inside the pores, this is a cross-sectional view here, are nanodiamonds. So the nanodiamonds are lining all the pores of the structure in 3 dimensions. So the red particles are nanoparticles of diamond. So you can imagine a very large porous structure that you can flow things through, and then you can make interesting sensors for ionic liquids by using these nanoparticles as sensors. Here's a blow-up view, but there are nanoparticles all around the walls here. Another example that I won't have time to tell you about is you can take these nanoparticles and put them inside droplets. So these are microfluidic droplets of water and oil. So this is water and oil droplets. And you can see this is a bright field view, fluorescent view, and you can move these droplets around in whatever arbitrary pattern that you want. And inside the droplets are these nanodiamond particles undergoing Brownian motion. And then inside the nanodiamond particles are the polarized carbon-13 spins that have this long-lived pre-thermal state. So, it's like another dimension. And now you can make interesting types of sensors with this. And in this paper just came out, we showed most sensitive detection of ions with these moving sensors that I won't have time to tell you about today. And here is some other newer work on this. We take a single droplet and we can track the motion of the particles in real time. So this is time on this axis. You can see the particles moving around. And this motion is a time-encoded motion. So here you have a movable sensor, and it's moving around in space, in this case in Brownian motion, but the sensor also has these spins inside it that have these very interesting properties. Okay, I'm going to skip this. And finally, it turns out that I was telling you a lot about these diamonds, but it turns out there's a whole analog of these sensors that can be created in molecular systems. So this is also a large effort in my group. I won't have time to tell you about this, but the exemplary system is what's called pentacene. It's 5 benzene rings that you can dope in a system like naphthalene, like mothballs. Literally, it's like mothballs with pentacene in it. And it turns out that these systems have exactly the same properties as diamond. In fact, even better properties, because the T1, the nuclear T1, after spin polarization is 800 hours on these systems. So 800 hours is basically 2 months, which means that you can polarize it now and then maybe come back in March and it will still be polarized. And then you can possibly have these long-lived states that live even longer because T1 is very, very long in these systems. Okay? And this is kind of what we're working on. You can grow very large crystals at home, in your lab, and this crystal costs $3, and this crystal from De Beers will cost tens of thousands of dollars. So you can also create new types of molecular frameworks with this, and so on and so forth. So it's really a toy store of things you can do because it's a molecule that's a sensor, and you can construct interesting, complicated scaffolds with it. Okay, so let me end here by saying that what I tried to show you was this pre-thermal phenomenon is very interesting because you can arrest thermalization to some order of some power series. You keep the spins alive for a very long time. You can watch them in real time, but not only are you keeping them along one axis, but you can move the axis around, so you can make interesting like 3-dimensional shapes. And then you can do interesting things with that, including sensing. You can make time crystals, and you can measure these in one shot. You can create a spatial structure and keep that stable for a long time. And all of this can be done in platforms that you can move inside objects or onto objects. So kind of interesting combination of traits that maybe has a lot of interesting potential in the future. Okay. So I'll end with that. I just want to show you the group of people who worked on all these projects. So I represent Berkeley and Berkeley Labs, so staff scientists, postdoc students, and a large number of undergraduate students at Berkeley, a large number of collaborators, and all the funding agencies that help to provide funding for this work. So thank you.
So thank Thank you very much, Ashok. So we had two wonderful talks. I mean, what is happening at the forefront of the theory in open quantum system and the experiments, particularly quantum sensors, where they are going. It's beautiful. But now, before we take in all the questions, we will go for a coffee break. And after half an hour, 4:30 exactly, we will begin here again. And your questions you can submit. And also just one more request, I mean, when you are asking the question, if you just introduce that my name is and I am from, and because we are live streaming, so it would be very good if you introduce yourself before you ask the question. Thank you very much.
Just one little thing. I will be collecting questions sitting here, so you can give your name to me. I'm not collecting questions, only the names.
The next session starts at 4:30. Now this clock is now okay. So